now we're going to introduce this concept of a sampling distribution. And this is how we're going to introduce probability to measure the uncertainty that we're going to have in our inference by just looking at the information in the sample, and on the basis of that, talk about what's happening for the population. All right, what we're going to do is we're going to this website, which is run by the statistics department at Rice University. So when you get there, you see this and click on begin, and this is what you're going to see. So we have before us a population, and that is the top panel here. Then what we're going to do is we are going to take a sample from that population, and you will see the sample displayed here. And then what we're going to do is we're going to keep a running summary of what we saw in our samples, because we're going to do the sampling repeatedly. Now, in reality, of course, we only take a single sample most of the time. But for now, to get this concept of a sampling distribution under our belts, let's think of taking repeated samples. Okay? And what we're going to do is keep the summary here. Now, whatever population we have here, they take some summary measures over here. So for example, we see the mean. So the mean is 16 for this population. The median is 16. The standard deviation is 5. And then there's a couple of other things here called skewness and kurtosis. I'll leave that. I'm not going to be addressing that. I'll leave that up to you to look up if you're interested. Okay? And this one, for now, we're going to ignore this panel here. So we are here, and let's start choosing things. So we've got a set of statistics we could look at. Let's stay with the mean. We have to decide on a sample size we want, let's say 25. Now, let's look at the population that we have up here. We can choose the normal, or they can let us look at the uniform, or they can let us look at a skewed population, or we can make up our own custom population. Let's do that. Let's just make up a custom population. So here's the distribution of the population. It's some, I just made it up. I just love to do it with this, and things work nicely. So this population has a mean of 15.56, a median of 15, and a standard deviation of 6.71. Okay, now what we're going to do is we're going to take a sample from this population. That's what happens when I click the animated. And remember, we chose a sample of size 25. So here are 25 observations from that population. And here they range pretty much over the whole range, just like the population. So there's one value down there, there's another value there, there's a value there, there's 3 values there, and even right at the extreme right-hand side, we've got another value of 32. Now, the mean of these values is 14.4. So the sample mean is 14.40, the mean of those 25 observations. Okay? Now, what this software is trying to do, remember, we're trying to estimate the mean of the population, which is 15.56, on the basis of this sample of 25 observations. And the mean is 14.4. What the software does is also retains that mean, the mean of the sample. Let's take another sample of size 25. This time we'll get another mean. This mean is 16.06. We could use this to estimate the population mean of 15.56. Or, what it also tells us is the mean of the 2 repetitions that we've taken so far. The mean of those 2 is 15.23. So you've got 3 means on the screen. The mean of the population, the mean of the current sample, in this one, with the third time we do it, is 14.17. And then the mean of the means, the mean of the three means, 14.88. It looks like that mean is getting closer to the mean of the population, which is 15.56. We can speed this up. We can take 5, so now we've done it 8 times. And we see that the mean of those 8 is 15.63. We're getting closer to the mean of the population, which is 15.56. Okay, let's now recap what we have. We've got the mean of the population, 15.56. We've got the mean of the current sample, 16.22. And we've got the mean of the means, 15.70. Okay. Now, we could keep on doing this, and but let's just do it 1,000 times. So here we go, 1,000 times. And now the mean of the means is 15.61, as opposed to 15.56, which is the mean of the population. Let's do it another 10,000 times. Okay, and now the mean of the means is 15.57. We're getting about as close to the mean of the population as we're going to get. So it's 15.57. Okay, now the other question is, let's look at the mean of the means. They look tighter. They look closely, more closely bunched together than the population. The population is spread out all across the line there, whereas the mean of the means is very much tighter. So what measures the spread of the distribution? Well, the standard deviation. Now, the standard deviation in the population is 6.71. Whereas the standard deviation of the means is 1.35. So what's the relationship between those two? Well, if you divide the one by the other, you'll get about 5, which is the square root of n. So the theory tells us that the standard deviation of the sample means, this one, should be about 1/5 of that one. And indeed it is. It's about 1/5 of that. Okay, that is called the standard error. The standard error is the standard deviation of the sample means. Okay. One last thing is, what is the shape of this distribution at the bottom? And theory tells us that that should be approximately normal. Here I've clicked on fit the normal, and there it is, and you can see that it's a pretty good fit. Let's go up and let's look for a skewed distribution. Let's jump to 10,000. We'll see that the shape is pretty much the same. You can do the calculations on the mean and standard deviation. If we have a uniform, pretty much the same thing happens. The shape is close to normal. And if we have the normal distribution, once again, the shape is pretty much normal. That's the magic of this. We always get this normal distribution when we look at the distribution of the means, of the sample means, from whatever population we get. If the sample size is big enough, here we took 25, if the sample size is big enough, we're always going to get this normal distribution at the bottom. So let me summarize. We've got a population. It has a mean mu, standard deviation sigma. We don't know what these values are, typically. And what we'd like to do is find out, let's focus on the mean for now, find out what is the value of this population mean. Then, what this concept of a sampling distribution is first of all, take a sample, then calculate the mean of the sample and discard the sample and just retain the sample mean. Do this again tomorrow. Take another sample, keep the sample mean, get rid of the original observations, and keep on doing this repeatedly. Okay? So what we've got, population has a mean mu, standard deviation sigma. We typically reserve Greek letters for the stuff we don't know, or the stuff that refers to the population. So population has mean mu and standard deviation sigma. We're going to take a sample of size n, except we're going to do it repeatedly. So we take samples of size n. Once again, typically we just take one sample. But for the moment, since we're talking about sampling distributions, let's talk about repeated samples. And then for each one of these samples, we're going to get a sample mean. And let's talk about the distribution of these sample means. So this is the third panel at the bottom. Let's talk about that. Well, that distribution has mean mu, which is the same as the population distribution. Okay, so that's result number one. And theory tells us this is so. We just saw a demonstration of this. Okay. Has standard deviation, or standard error, sigma over the square root of n. So it's the population standard deviation, but it's made much smaller. It's divided by the square root of the sample size. So when we're thinking of how does the sample mean vary from sample to sample, okay, it has a mean which is the same as the population mean. So that makes sense. We're going to vary around the same thing as the population. Number two, though, it varies much less than just values in the population. And the factor by how much less is the square root of n. And it's normally distributed, or has a bell-shaped curve, whatever. Now, this is technically true as n goes to infinity. So that is the theory. Now, it actually turns out that the closer the population distribution is to itself being bell-shaped, the faster infinity gets approached. Okay, so that we can get away with a smaller sample to make this statement. This theorem here is called the central limit theorem. Okay, it actually is central to just about all the inference we're going to be making in this course. It's extremely important. So make sure you understand the meaning of what we've been saying up to now. This is the central result that you need to understand. So go to the Rice site and experiment for yourself with this result. Let's take a look at an example. So in our population, the total cholesterol level at visit 1 had a mean of 237 and a standard deviation of 44.7, rounding things off. All right. Now, if we take repeated samples of size 25 from this population, what proportion of these samples will have a mean that's greater than 260? So we have the population, mean is 237, standard deviation 44.7, because we know what the population is that we're sampling from. That's not how things typically work in practice, but for now, this is just an intellectual exercise that we're carrying out. So we've got this population with a mean of 237, and the question is, how often will the sample mean, not the population mean, how often will the sample mean, when we take samples of size 25, have a value bigger than 260 or equal to 260? Okay, so here we have it. We can use the central limit theorem because we've got a population with mean 237, standard deviation of 44.7, and we're going to take the sample mean, and we know from the central limit theorem that those, if we do this repeatedly, that those sample means will be distributed around a mean of 237 and a standard deviation of 44.7 divided by the square root of the sample size. So that, which in this case gives us 8.94. So that allows us to answer that statement, that question, sorry, of how often do we see more than 260. So let's go back to our standardized variate, z, which is the variable we're interested in minus its mean divided by its standard deviation. So the variable we're interested in is x bar. So we're asking the question about 260. When is it bigger than 260? Let's standardize that by subtracting its mean, 237, dividing by its standard deviation, and the answer we get is 2.57. So the question asked about x gets translated into a statement about z, asking how often is z greater than or equal to 2.57. So we go to Stata and we ask for 1 minus the normal of 2.57, because normal 2.57 gives us the probability of being less than or equal to 2.57. So 1 minus that will give us the probability of being greater than 2.57, and there it is, it's 0.005. So we can answer the question, the probability of getting a sample of mean of 260 or higher when taking a sample of size 25 from this population is about 0.5%. So it's something that will happen probably once in 200 times. Okay, so this might be our definition of a rare event. So very rarely will we see a sample mean of 260 or bigger. What do you mean by rarely? This is what I mean by rarely. In this situation, probability of less than 0.5%. 1 in 200. So that is how we use the central limit theorem.